There's a battle going on out there that will determine the fate of the universe. It's a battle between two great forces, one trying to pull the universe together and the other trying to push it apart. We travel to when time began to find the universe in a beach ball.
Thanks for passing me the universe.
We go down a mine to look for what's pulling the universe together.
If you're an astronomer and someone says you don't know what 2/3 of the universe is made from, that irritates you.
And we look for what's pushing it apart by searching for exploding stars. Oh, I finally. I'm Alan Alda. Join me as Scientific American Frontiers ventures out into the dark side of the universe.
This program was made possible by the National Science Foundation, America's investment in the future. And by contributions to your PBS station from viewers like you. Thank you.
Once we thought our world was the center of the universe. And today, we know we're on a minor, if privileged planet, circling an average star in an inconspicuous spot in an unremarkable galaxy that's just one of billions of galaxies, occupying a universe that stretches farther than we can see, even with our biggest telescopes. But in the last few years, telescopes like these here in Chile have shown us that we're even less at the center of our universe than we could have ever imagined. You and I and these rocks and the sun that shines on us and the stars that twinkle overhead aren't even built of the same stuff that most of the universe is made of. And there's a mysterious force out there in space that literally comes out of nowhere. It's a force that seems to be pushing the universe apart faster and faster, until one day everything out there beyond our own little solar system will simply disappear into blackness. Our universe and our place in it just got a whole lot weirder. Staring at a patch of sky 1/10 the diameter of the moon, the Hubble Space Telescope recently peered farther out into our universe and farther back in time than any telescope before. For 1 million seconds it gazed, gathering light from 10,000 galaxies. The smallest and faintest are some 13 billion light years away, meaning their light has been traveling toward us since shortly after the universe began. What gave birth to these first galaxies is one of the great mysteries of our cosmos. But astronomers now suspect that matter we can see in the universe, including ourselves, resulted from a titanic struggle between a form of matter we can't see, dark matter, and a force, dark energy, that we've only recently detected. Together, dark matter and dark energy rule our universe. And we're here to wonder about them only because in their battle for domination, which has gone on for most of eternity, neither has triumphed.
2, 1, main engine start, and liftoff of the Delta II rocket with the MAP spacecraft, exploring the past and future of our universe.
This was the launch on June 30th, 2001, of a spacecraft able to look even farther back in time than the Hubble. Called WMAP, its mission was to capture the very first light of the universe. That light has been traveling toward our own little corner of the cosmos ever since it was released from what most astronomers now agree was the origin of everything we can see. Planets, stars, galaxies like our own Milky Way, and the billions of other galaxies that have been expanding outward since the beginning. That beginning was the Big Bang, a ripping open of space and time, inflating in an instant to become an unimaginably hot cauldron of energy and matter. It was light escaping from that cauldron that WMAP was sent to measure. Light now reduced by its journey through eternity to a faint afterglow called the cosmic microwave background radiation. What the satellite saw has been mapped onto something I can comfortably get my hands around, if not yet quite my head. this device, this satellite, is picking up this cosmic background microwave radiation from way back in time.
Right.
Right? From the beginning of the universe.
It's actually a direct picture of what the universe used to be like because it took that light all that time to get from there to the satellite.
Okay, here's the you have to help me visualize this.
Okay.
A lot of us, when we first hear about the Big Bang, think of it like an explosion happening in a point in space and moving out. And then somewhere we're in that or something. And a lot of us think when we look back in time, we want to look back to that point. But on the contrary, when you look back in time, you're looking in every direction. You're looking all over some shell.
Exactly.
And everywhere you look, it's as far back as you can go. How could that be? Can you explain that? Can you give me an image that helps me grasp that?
You're trying to think of an explosion that happened in one place.
Yeah.
And instead, the universe was... Today, it doesn't have any particular center, and it never did. Everywhere you would have gone, it would have been expanding.
Yeah.
I like to think of baking a loaf with little raisins in it, and when the bread rises, all the raisins are moving away from all the other raisins. No raisin can really claim that it's in the center of this expansion any more than any other, right? And this is the same way we need to think of our space.
I know, but here's the problem. Every time one of those raisins wants to look at another raisin,
Yeah, it feels.
it can look all the way across the loaf to a raisin on the other side, but if it looks in the other direction, it sees the baking tin. That's a little bit different.
That's because the bread is finite, and we live maybe in an infinite space. If you live in an infinite loaf of bread, there's nothing you can do to tell the difference.
The picture of an explosion and a ball of stuff is, I agree that that's what many people think of, but that's just wrong. It's not what the Big Bang Theory is all about. What the Big Bang Theory is all about is space itself. Think of it as being stretchy, and it's just constantly stretching, and it's stretching between every object everywhere, so that everything is getting farther away from everything else. And no matter where you are and you look out, you see a glow left from the
So
initial
it
Big Bang.
needs to be called the Big Taffy Pull.
Well, that would be a better name. Almost anything would be a better name.
The infinite, then.
The infinite taffy pull.
Yes.
Okay, well, I think you're getting me closer. All right. Okay. Show me what the implications of this mapping are.
So what I really love about Chuck's beach ball is that it represents this very basic fact that even though space itself may be infinite, we can only see a finite volume. It's a huge volume. This is about 13 billion light years in radius, but it's still only finite, right? So we're in the center of this, and the most distant thing we can see is this hot glowing wall of hydrogen plasma, which is opaque. So, we just can't see what's on the other side.
But on the side of the wall we can see, on our beach ball, it's the inner surface. The incandescent plasma just beyond has cooled enough to go from being uniform and featureless to having eddies and ripples. It was these tiny imperfections that were imaged by the exquisitely sensitive eyes of the WMAP satellite.
Chuck and his colleagues have stretched the contrast here by a factor of 100,000 to prevent it from looking completely uniform. But there are, nonetheless, these tiny ripples where some places look hotter, others look colder. And that's just because there was a tiny bit more stuff in some directions than in other directions. And these little ripples are extremely important because it's because of them that we're here. If you just had something which was always uniform, it would stay uniform forever, and you would never make clumps, planets, and we couldn't be here talking.
To find out more about how those faint early ripples left over from the Big Bang became our universe, we've come here to the foothills of the Andes in Chile. This region has become home to some of the world's biggest and most powerful telescopes. Lured here by clear skies and a smooth flow of air off the Pacific Ocean that reduces atmospheric turbulence, making for what astronomers call superb seeing. This is the site of one such observatory, Las Campanas, run by the Carnegie Institution of Washington, and the principal research site of an old friend of Frontier's, Alan Dressler.
Well, welcome to the Las Campanas Observatory, Magellan telescopes.
Thank you. There seem to be two.
There are two. They're twin 6.5-meter telescopes, which means they have mirrors that are about 22 feet across. which is a good size, and they collect light from distant stars and galaxies. And this is where we do most of our research. Hi, Miguel.
Hey, how are you?
That research is focused on the formative years of the universe.
At the beginning, we know there was a very simple distribution of matter. It was very smooth. It was very simple elements, hydrogen and helium. There were no stars, just gas. How did the universe go from being deadly dull with no variation to tremendously complex so that there are creatures on it that look back and figure it all out? That's the fundamental question. And this zone, this sort of 3 billion years in to maybe 8, is where most of that complexity grew. And we can see that evolving, happening by this strange ability to look back in time. I mean, only in astronomy can you actually look back and see 5 billion years, 10 billion years into the past. You can see the past because it took the light.
All those stories about time machines.
Yeah, it is.
We got one. We're looking at. The light from the stars comes in and hits that mirror.
Exactly. Gets reflected on another mirror that's above
that
us
little guy
here.
up there.
The little guy up there, which in turn reflects then the light through the hole in the black turret where there is another mirror, a diagonal mirror, 45 degrees, which directs the light to the instrument.
When the light hits that mirror, how long has it been traveling?
Well, for the things that I'm looking at with Pat tonight, the light has been traveling for about 10 billion years. So pretty much the whole age of the universe. And this is the first thing it hits after all that time. So it's got to be cleaned.
Especially tonight, because it's the first time Alan will be using a brand new instrument.
Alan, this is Pat McCarthy, my science partner here. This is the slit mask.
So if you turn around and look through the light, you'll see.
In what they affectionately call the WOC, Pat has painstakingly cut tiny holes corresponding to the galaxies he and Alan plan to study.
In any area of the sky that we pick up, say 1/2 degree across, that's what this is looking at, that's the size of the moon, there will really be 100,000 galaxies, very faint, very distant galaxies. And we have selected, in this case, 700 of them we want to look at. So we must make sure that the light from those 700 goes through the spectrograph, but nothing else.
Alan's new instrument doesn't just take pictures of those distant galaxies, it can read their spectra. In fact, nearly everything we know about stars and galaxies comes from analyzing their light with the aid of a prism, or more commonly, a device called a diffraction grating.
When sunlight or any light strikes this, it's spread by color into its component colors. You can say how much red light, how much green light, how much blue light tells you something about the temperature of the sun. And the sun is a star at 5,000 degrees temperature, produces a lot of yellow light. And so the middle of this spectrum and the most intense part is yellow-green.
And then we can see almost with our bare eyes. We see red stars and bluer kind of stars. That has to do with the temperature of the star, basically.
Here, for example, in one of the first images taken with Alan Dressler's new camera, both red stars and blue stars are visible in a galaxy nearby. But in the spectrographs that astronomers use, the colors of a star can be analyzed in much finer detail than is visible in a rainbow. There are lines at precise locations across the spectrum that reveal what a star is made of, as well as its temperature and its size.
The reason that's important is different stars of different size last, they live a different amount of time. The sun will last for 10 billion years. It's halfway through its lifetime. A star much more massive than the sun might only live for 1 billion years. So if we find those, we know that those are young stars. They cannot be any older than 1 billion years old because they would already be gone. So when I look across our galaxy, I could do them one by one. I could tell you what each individual star is like. I could see a star like the sun all the way across our galaxy. And if I put together the light from billions of stars, I could see them all the way across the universe. And in that information is the rate at which new stars are being born in that galaxy. 3 billion years ago, 5 billion years ago, 7 billion years ago. So I begin to build up a picture of how rapidly were galaxies turning their gas into stars over their lifetimes. A complete construction project.
At twilight, the Magellan Telescope's dome is opened.
We need to rotate 0.335 degrees. Plus 0.335. Trace, 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 cinco.
So how many galaxies are going to have their spectra taken?
We're going to take spectra of 700 galaxies tonight.
700.
Yeah, that's probably as many as ever been done. You got to remember to put in the walk, because that's a big mistake. If you don't do that, you really blown it.
This first exposure using the wok took a half an hour.
Okay, so already we can see some objects. That's encouraging. There's a bright one.
This is just the beginning of several months' work that will add up to some 50 to 100 hours of data. But even from these first few minutes of peering across the universe, a trickle of light has left the signature of a galaxy in the full fury of creation.
So here is a very faint line that is a very faint galaxy, very far away. And here at this one color, that represents probably 100 photons of light coming from a place where 1 million hot young stars have formed in that galaxy 10 billion years ago.
So it's 10 billion years ago, and all that made it to us tonight were 100 photons.
That's right.
So this is the first scientific run you've done, huh?
Yes. New instrument.
How do you feel? Is it a good start?
It's a good start. I wish we had seen a lot in the first exposure, but you have to have a lot of patience if you're going to do something really hard. But it works. The instrument works. It's producing spectra.
You've been working on this instrument for how long now?
6 years.
6 years.
It took a long time to build, but now it's going to pay off for us.
That payoff will help illuminate one of the universe's darkest secrets. How those early ripples left from the Big Bang became the seeds of the stars. A vital clue to that mystery was discovered because a little girl loved watching the movement of the stars in the night sky outside her bedroom window. That story next. In the early 1970s, Vera Rubin was a rare young woman in the traditionally male-dominated world of astronomy.
I got interested in astronomy by watching the stars as they moved outside my window. I had a window that faced north. I had a bed under the window, and I could see during the night that the stars changed their positions, and that's really what got me interested in astronomy. So I guess I was always interested in how things moved.
Vera decided to look at how stars move in spiral galaxies, like our own Milky Way, as they revolve majestically in space. Most astronomers then studying galaxies were drawn to their centers, where the stars are densest. But as a then shy young graduate student, Vera looked instead to where galaxies trail off into empty space.
I had children, and I didn't want to compete with what other people were doing, so I decided to study the outsides of galaxies.
What she discovered there was revolutionary in both senses. In our solar system, the planets revolve more slowly the farther they are from the gravitational attraction of the sun. Galaxies were assumed to rotate similarly, with stars moving more slowly the farther they are from the center. Instead,
I found that the stars very far out were going just as fast as those near the center, sometimes even faster.
Sometimes faster.
Sometimes faster, and well beyond where there was no light. In fact, I went to my office this morning and got this. Here's Andromeda, which is the largest galaxy, largest spiral near us. At our position in our galaxy, which would be like maybe a third of the way out here, we're moving at 500,000 miles an hour around the center of our galaxy.
You hardly feel a wind.
That's right. And you don't notice it because everything around us, all the stars near us, everything is going just at the same speed that we are.
Yeah.
So here are the velocities of stars and gas all the way across. Newton's laws, because this is where the luminosity is, would predict that the velocities rise and then fall rapidly, so that by the time you get out to what looks like the edge of the galaxy, the stars would be moving almost negligibly, very, very slowly. So what you see instead is they're moving very, very fast, all the way out there.
So when you got that information, then what did you think you were wrong, or did you?
No.
You knew you were right.
I never thought I was.
Everybody never thought you were wrong.
I never thought. No, I had some crazy ideas, and then it shortly settled that what would have to be was matter that isn't luminous, that you don't see. The galaxy has to extend that far out. There has to be something. There has to be matter that's gravitationally accelerating the little bit of gas that we could see.
There had been hints of invisible matter in the universe before, but Vera Rubin's startling discovery confirmed it. Her observations implied, in fact, that galaxies are embedded in immense halos of dark matter, invisible to our telescopes, and yet making up most of the actual mass of each galaxy, including our own.
The whole concept of dark matter is enormous. It means that when you're looking at the sky, you're only looking at a few percent of the universe, that most of the universe is invisible.
To look into one of the possible sources of this invisible dark matter, we've come to California and the first mountaintop observatory ever built, the Lick Observatory, dating back to 1888.
The founder is buried at the base of the telescope. Yeah. James Lick is buried at the base of the pier here.
Does anybody ever think about that when you're in there?
I used to think about it when I was observing at the 40-inch down the end of the hall, and in the middle of the night the wind would come, whirring through the hall, and you'd hear the clanking of the old heaters, and yeah, I was pretty sure he was coming down to visit me.
The original telescope here is still used to look at planets in our own solar system.
We can open up the telescope and work.
But Deborah Fisher is hunting for planets well beyond its range. In fact, for planets around other stars.
So this is the little collecting mirror that we're going to use tonight. The starlight will come down and hit the mirror and is reflected up through that trough, slides up there, and goes through that hole in the side of the dome. Looks like fun, right? We want our photons to have fun. So the light that we saw, the light path outside.
I love these little mechanical things.
That's right.
It's like something from Jules Verne.
Exactly. But the magic part of our whole project really is this iodine cell. And now as the starlight passes through this cell, the iodine is absorbing starlight at particular wavelengths. And so finally, in the spectrum of the star, etched into the spectrum, we have a forest of iodine lines, thousands of them. And so it's essentially like a grid on our spectrum.
Deborah is looking for tiny telltale shifts of a star's signature spectrum against that fixed grid of iodine lines. A shift that betrays a star's moving toward and away from us due to a planet's tugging at it. This backward and forward wobble also reveals the planet's size in orbit. The bigger the wobble of the star, the more it's doing that, the bigger the planet is going around it, and the faster it wobbles, the closer it is.
That's exactly right.
Yeah. Okay. So in that way, you can really tell us what's there.
That's right.
Deborah and her colleagues have found some 70 of the over 100 planets so far discovered orbiting other suns. Most of these planets are huge and orbiting fast, making their detection easier. Deborah's team's most dramatic discovery attracted the attention of a 4th grade class in Moscow, Idaho.
And when we found this system, this first star with 3 planets, they sent me a letter, Dear Dr. Fisher, we've been reading about this discovery in the newspaper, and we're doing, scale models of the solar system with paper plates, but we wondered, if you'd named the planets yet, because if you haven't, we have a suggestion. And so they said the planet that's 4 times the mass of Jupiter should be called Forpiter. and the one that's 2 times the mass of Jupiter should be called Tupiter, of course. And then the little one that just orbits every 4 days should be Dinky. So.
The star that Deborah's observing tonight, she's already looked at some 200 times. And while it used to be thought an unlikely candidate to have a planet, she's now picking up the faint trace of a wobble. Planets are thought to form from disks of dust and gas that surround the sun. And it could be that many of the billions of stars out there have planets so far undetected. The fact that you're looking for planets that so far haven't been seen, mostly, is that some of the missing matter, or what?
That's a good question, and that's one of the early hypotheses, was that maybe the dark matter is just planets. After all, we now believe that planets, when they form, some of the planets fall inward, but others are ejected from their solar systems. And the best way to get a handle, sort of a back-of-the-envelope calculation, is to look at stars that are forming, being born out of molecular clouds, and to imagine that all of the material in these typical disks around the stars is ejected. Let's just take that as an approximation. And then, would that be enough to make up all of the missing mass? And the answer is no, that the calculation has been done, and that it probably isn't, it's orders of magnitude too low to account for the missing matter.
In fact, not only is most of the missing matter in the universe probably not the stuff that stars and planets are made of, it's probably not the stuff that anything is made of. Here on the Yorkshire coast of northern England, the search for dark matter has gone underground. This is the Boulby Mine, whose mile-deep shafts provide cover from something tantalizingly similar to the prime suspect for missing matter.
And if you're standing on the surface of the Earth and you put your hand out, you get hit. 1 cosmic ray a second goes through your hand, and that would spoil the detector signal that we're looking for. So we go deep underground, and then the large amount of rock between us and the surface shields us from the cosmic rays. So when we're down in our labs, rather than 1 a second going through your hand, it's 1 a week.
But while cosmic rays are exotic, at least they're made from subatomic particles that science is familiar with. By contrast, the things Nigel Smith is trying to detect are bizarre even to physicists. Here, a mile down in a vein of rock salt mined to spread on the winter roads of northern England, he's in a race with some half-dozen groups set up in similar underground labs around the world to be the first to detect what are called, with tongue-in-cheek, WIMPs, for weakly interacting massive particles. WIMPs have the apparently paradoxical property of being massive in the sense that they exert a gravitational tug, while being almost completely unable to connect with ordinary matter in any other way. In fact, to call them weakly interacting is to be generous.
Most of them pass straight through the Earth and don't even notice. Most of them pass straight through the Sun and don't even notice. But every so often there's just 1 or 2 a month or a year will actually hit a nucleus head on. And that nucleus recoils, and it's that recoil that we're looking for. But the majority of the billions of WIMPs that are passing through as we stand here every second, they just stream straight through, and you never see them.
This is just one of 3 different kinds of detectors here at the United Kingdom's dark matter hunt. And the research project has just constructed a large new underground facility to house them. There are other detectors in tunnels beneath the Apennine Mountains in Italy, where a joint Italian-Chinese team has been claiming evidence for WIMPs, a claim met with skepticism from their competitors. While in the United States, a new facility is being constructed in a mine in northern Minnesota. All this effort to detect a hefty ghost particle that may not even exist. For those involved in the hunt, there's no doubt that it's worth it.
It's a fantastic question. If you're an astronomer and someone says you don't know what 2/3 of the universe is made from, that irritates you, right? So you want to go out there, you want to find out what it is.
And astronomers aren't the only ones in the hunt, which is why I find myself driving a golf cart through the longest building in the world, the Stanford Linear Accelerator in California. I'm following the track of a subatomic particle as it's accelerated during its 2-mile trip to a speed approaching the speed of light. Eventually, the beam of particles will be divided and spun around a couple of loops before crashing head-on into particles coming in the opposite direction and smashing into smithereens. We're visiting the collision point, appropriately, with both a particle physicist and an astronomer. The beam of particles will come down here and go through that pipe.
And then you hope that an electron and a positron will meet, annihilate, and new particles will be born.
It's from collisions like this that scientists have built up their picture of the fundamental particles of matter in what they like to call the Standard Model. But for the Standard Model to work, physicists have been forced to invent a strange mirror world in which the known particles have ghostly cousins called supersymmetric particles.
This extra set of particles we haven't discovered yet, but they're our best candidate. We think it's the smoking gun for the dark matter out there. So you and I aren't made of these supersymmetric particles, but the dark matter that's controlling a lot of what's happening in our universe is made of these supersymmetric particles.
That's the best theory.
That's our best guess at this point.
Now, this is interesting. You are pretty sure, or are you dead certain, that these that supersymmetric particles exist or have existed?
We're going to get different answers.
Less than pretty sure, but if this were a horse race, this is the one I'd be putting my money on.
It is thought that supersymmetric particles are all over the universe?
They're out there.
Yeah.
Yes.
And how did they get started? Where do they come from?
On the Big Bang itself.
From the Big Bang. So are you trying to create a situation something like the Big Bang, where you get both the particles and the supersymmetric particles, the mirror versions of them? But I thought you needed something I thought you needed a lot more energy than you could possibly get on Earth to create a Big Bang.
We're not recreating the Big Bang.
Right, thank God, because I would stand a lot further away from it, and I'd wear that hat.
But we are able, if we have enough energy in our particle accelerators, to create the constituents that were created in the Big Bang.
And so, at the same time that astronomers are going underground in their hunt for the missing dark matter, particle physicists too are burrowing to build the biggest atom smasher ever in the hope of creating dark matter. This is the construction of what's called the Large Hadron Collider at CERN in Switzerland. Due to come online in 2007, the LHC will have gigantic detectors designed to peer into the wreckage of particle collisions of truly stupendous energies. If not quite the Big Bang, then certainly the closest we've ever been to it. The closest we've actually been to it, of course, was with the WMAP spacecraft, which mapped the ripples left as the Big Bang cooled. In the pattern of these ripples, the WMAP scientists see direct evidence for dark matter.
You only get this if you have about 6 times more dark matter than all atoms combined.
What we did is we generated literally tens of millions of possible universes on the computer, and we compared them with our measurement of the real universe that we have. And I think of it as like matching fingerprints. So this is the actual fingerprint of the real suspect, and we have a mug book of fingerprints, and we match them up, and we pick out the right suspect that way. And as Max described, that the right suspect has this substantial amount of dark matter in it.
Today, then, the evidence is mounting that most of the stuff in the universe is not only invisible to us, but isn't even what the visible stuff is made of. But to astronomers like Alan Dressler, looking back in time to see how the universe began, dark matter is more than just astonishing. It allowed us to be. You're taking this picture of way back in time, and you're seeing the formation of the stars. Now, what role does dark matter play in that?
It's very important to see how galaxies form, but they couldn't have formed, we now believe, without the dark matter, because there wasn't enough gravity and all this kind of material that we're made of to coalesce and make stars. And that's where the dark matter played the pivotal role. It actually held this, what we call baryonic normal matter, together and allowed it to begin to concentrate and to cool and then make stars. So that transition from, already there were these sort of wells, these places where gravity was strong, and all those atoms suddenly said, oh, there's gravity here from this dark matter, and they headed in that direction. So they fell into those little wells of gravity that have been growing since the Big Bang.
But if dark matter's gravitational hug was indispensable to our universe's birth, we now know that from the start it's been opposed by an anti-gravity force that might, if things had turned out just a little bit differently, have overwhelmed it, and instead blown the infant universe apart. That story next. In the early 1990s, two groups of astronomers came up with a new idea for discovering the ultimate fate of the universe. Both groups, which were soon to become rivals, used several telescopes in their quest, including this one at Cerro Tololo in Chile.
They've had their nights on the telescope, sometimes actually immediately after our nights, or in between our nights.
So do you go around looking for scraps of paper the other ones left, or what?
No, sometimes we look at, we try to figure out what they've observed, but usually it's a friendly rivalry.
Both teams used the telescope to look for the same thing, the death of a star. But not just any stellar death. A particular kind caused when a companion star dumps material onto a so-called white dwarf until the white dwarf reaches a critical mass and explodes. This is called a Type 1a supernova. And the astronomers like it because all Type 1a supernovae are almost exactly alike. Identical flashbulbs popping off randomly all over the sky.
With just a 2-minute exposure on this telescope, we can see halfway across the universe. That's how powerful the telescopes are and how bright supernovae are. So we can take very short exposures and cover large parts of the sky to discover supernovae.
But discovering them is only the beginning. Once a supernova is spotted, other, even bigger telescopes are standing by to pounce on its light and read its spectrum.
If we don't find supernovae in this telescope, then all the other telescopes who are waiting have nothing to do.
Right.
They get real mad at us.
Is this the first time you're observing in this test?
Yeah, this is the beginning of our season. So we're going to go 3 months now, 30 half nights searching for supernovae. And tonight is the first night.
So your exposure is covering all of this, and that's even more than a full moon would be in the sky. So what's the probability that you'll find a supernova?
In this one field?
Yeah.
It's about 1.
It's one for this month.
Yes.
But so sometime during this month, you're going to, if you keep pointing there, you're going to catch at least one.
Oh yes, yeah, definitely.
Yeah.
So now the telescope is slewing. So the stars are whipping by.
Here's a cool image. This is the first image that came off tonight. And so you can see lots of galaxies, very faint galaxies, stars. Here's a very nice spiral galaxy here with disturbed arms. So you're going to observe, right?
You mean more than I am now?
Yes, right here.
You want me to actually
sit here? Yes.
The end of science as we know it. All right. Okay. Well, let's see. I'll just hit a few keys here.
Oh, no way.
I just like to poke around. Yeah. That's how I learn. You know. What should I do first?
Wait for him. When he says OK, you hit enter.
And that's it?
That's it, yes.
No. Okay.
Okay.
There it goes. There it is. And that sound was the shutter opening.
Oh, yeah. Yeah, I heard that.
Now taking data.
Your first image in search of supernovae.
Hope I find That first night of the season, Nick and Chris and their team took 16 different snapshots of the sky. By the next night, now no longer observing from the telescope but from a control room in the nearby town, they had processed several of those images. And one of them, though sadly not mine, came up a winner.
So here we've got a big diffuse source of light, and it looks like it's probably a galaxy. And in both the images, there's apparently a little new light source just outside that galaxy. That looks like a supernova to me.
Great.
this would be a really good candidate if we get a follow-up image to do spectroscopy. As a matter of fact, we don't need a follow-up image. This definitely is a supernova.
Supernovae are very rare events. The last one in our galaxy was 300 years ago. So it's only by staring at tens of thousands of galaxies at a time that the supernova hunters can hope for success. Once they've found one, there are only a few days before its explosion dies away. So there isn't much time for a large telescope like the Keck in Hawaii to get its spectrum. This spectrum not only confirms it's a Type 1a, but it also gives its age. The older the light, the more it's been stretched as space itself has expanded, and so the longer its wavelength, the more it's shifted toward the red. And because every Type 1a supernova explodes like a standard flashbulb, its brightness reveals how far away it is. And this is why both rival teams of astronomers were hunting so eagerly for Type 1a supernovae. By finding supernovae of different ages and measuring their distance, both groups hope to find the answer to one of astronomy's great questions. What is the ultimate fate of the universe? We met members of one team at Cerro Tololo. The other is based here at the Lawrence Berkeley Laboratory in California and is led by Saul Perlmutter. Both teams expected to measure how much the expansion of the universe has been slowing due to gravity, especially the gravity of all that recently discovered dark matter.
And we thought it was going to be a great project. We were going to find out whether the universe was going to last forever or not, or whether someday all the stuff in the universe, all the matter in the universe would slow the expansion down to the point that it would come to a halt and then collapse. And what we ended up with was, when we started looking at the data, it looked like there was very little mass in the universe. In fact, it wasn't slowing very much at all. And then as you really looked at the data, you started listening, it's not only not slowing much at all, it's not even slowing, it's actually speeding up. And that was a real shock, because it was not part of the original description of our project when we were planning to use the telescopes. It was way better than that.
Instead of slowing down due to gravity, the expansion of the universe appeared to be speeding up, as if under the influence of some sort of anti-gravity. The rival team was coming to the same mind-boggling conclusion. Was it an exciting moment, or was it just puzzling and
puzzling and concerning, because it wasn't the expected result. So I mean, we were expecting deceleration. So really, the knot twist up in your stomach, saying, "Okay, let's go back and do this again. Make sure this is right." Yeah. And you go back through the numbers once again. You go back through the numbers yet again. Now you're starting to believe, well, we're onto something here. Wow. And the whole group, we're distributed, and so the emails start coming in saying, geez, can this be right?
You don't want to come out with anything that's wrong, of course, in a scientific, a major scientific announcement. And so you're being so careful, trying to check, well, maybe it's this, maybe it's that, and you're looking at every possible thing. Finally, we came to the conclusion, well, we have to come out and say it.
Were you all getting it right around the same time?
Yeah, we announced at the same time in 1998 at a conference in Santa Barbara. And both groups came out, and we sort of knew that the other team was going to announce the same thing, and I'm never sure how we knew that. But we sort of did.
Wait a minute. Were you pointing your telescope in their window and looking at their papers?
Us? No, we wouldn't do that. No.
The fact that both teams got the same result, I think, gave people a lot of confidence that it wasn't just some mistake that somebody had made in their calculation, because they knew the two teams would have loved to have been able to get the right answer and show the other one what might have been wrong.
I have done it.
Not everyone was taken aback by the idea of a runaway universe. Michael Turner had actually predicted the possibility several years earlier, reviving an old idea of none other than Albert Einstein. Turner came up with a name for a force that could push the universe apart, dark energy. But its roots lay in one of Einstein's famous equations. The notion of dark energy was, as I understand it, something that he came up with and didn't really understand he had come up with it. How far off am I with that?
That catches a lot of it. I mean, in science, people were often confused. And so Einstein was confused about the expansion of the universe. His equations wanted a universe that expanded. And so he put in this fudge factor that canceled the attractive gravity of matter.
When just a few years later the universe was discovered actually to be expanding, the cosmological constant, Einstein's anti-gravity fudge factor, was no longer needed. He gratefully discarded it, calling it his greatest blunder.
But it's one of the wonderful things about science is when we are in this struggle to try to understand, we invent things. And once you take something out of Pandora's box, you can't put it back. And so this idea was laying around in our idea box, and it's sort of like anti-gravity. It's a repulsive gravity. And so it resurfaced again in trying to understand why the universe not is expanding, but the expansion is speeding up.
How did you come up with the name dark energy?
It's kind of a nice yin and yang with the dark matter. You know, so we have dark matter and we have dark energy, and they're fundamentally different, and that's, you know, matter is different than energy. And then, you know, today we have the battle between the dark matter and the dark energy.
There is one uniquely privileged spectator to the battle between dark matter and dark energy: the Hubble Space Telescope. Perched high above the atmosphere of Earth, it has a clear view of the supernova beacons used to track the universe's history. We went to visit the control room for the Hubble Space Telescope in Baltimore.
Nice to meet you. Welcome to the Space Telescope Science Institute.
Thank you. I can't wait to see you.
Yeah.
My guide is supernova hunter Adam Rees. Can you tell me what all these folks in here are doing? I mean, there's constant activity and chatter, and what is it all about?
Right. They're primarily monitoring health and safety. They're looking at telemetry. They're looking at temperatures and voltages of thousands of different components on the telescope and making sure they're all within their tolerances. They're looking at the heating on one side of the telescope when it's in the sun side. About once a week, we upload a whole week's worth of observations of what's supposed to be done that week to the telescope. And so if we find a supernova, for example, we usually have to find it by Tuesday, because Tuesday is a special day when they build the calendar for the next week. It's sort of funny. The light's been traveling for 11 billion years. It finally arrives, and it's got to arrive by Tuesday.
In March 2002, the Space Shuttle Columbia, on what was to turn out to be its last completed mission, installed a new camera on the Hubble, the Advanced Camera for Surveys.
This camera is much more sensitive to light, and it also has more area, so I have a better chance of finding a supernova every time I take an image in the sky.
Adam's plan was to look back with the new camera to supernovae exploding when the universe was young. He found some half dozen ranging in age back to 11 billion years ago. His hope was to find out if the universe has always been pushed apart by dark energy, or if it once had been reined in by the gravitational pull of dark matter.
We have roughly...
Adam Rees works closely with Mario Livio. Adam observes the universe. Mario comes up with theories about it.
Basically, you have the universe behaving something like this. At first, it is expanding against gravity, so think of it as if it's held back by some sort of a spring.
But it's getting bigger and bigger and bigger over millions, billions of years.
That's right. That's right.
And then at some point, it's
about 5 billion years ago, we think,
it stops slowing down, and instead of collapsing, well, that's what we would expect it to do: get that big and then come back, right?
Well, even if not come back, but at least go slower and slower and slower.
Right.
Instead, it suddenly starts going faster and faster and faster.
And you found out when it started going faster and faster?
That's right. We actually witnessed the transition from the more recent accelerated expansion to the earlier slowing expansion.
This turning point in the history of the universe came at about 5 billion years ago, when dark matter began losing its gravitational pull against dark energy's inexorable push.
You know, gravity decreases in proportion to distance. You know, if you double the distance, gravity becomes 4 times weaker.
Right.
This force that you get from the dark energy, when you make double the distance, the force becomes twice larger.
Oh yeah, yeah.
We think it's a property actually of the vacuum, and so when there's more vacuum between you and a distant galaxy, there's more of this dark energy.
So
the force is bigger.
there is a factor of an increase in the amount of dark energy that has a factor on the speed.
Yes, that's right. It's a little bit like a built-in spring in the vacuum, and as something gets further away, there are more and more of these springs connected, and it's harder to compress. In fact, they're pushing more and more, and so the bigger the universe gets, dark matter is losing its pull on the universe. Dark energy is gaining its push.
It's always been there, right? The question that's now obsessing astronomers, including Michael Turner, is what dark energy might be.
So we just don't know what it is. If it is like Einstein's cosmological constant, then it's just the energy of nothing. And according to quantum mechanics, nothing is not nothing. It's full of particles that are living on borrowed time and borrowed energy. We call
They pop into existence.
And then when the accountants come along, they disappear.
Right.
And so if it's the energy of nothing, it's always been there. And then we're in for a very tough bit of history in the future, because the universe will keep speeding up and speeding up and speeding up, and things will get farther and farther away. And instead of the beautiful sky we have today with billions of galaxies, we'll only see a couple. It could be that it's just a phase we're going through, that something's out of whack and that the dark energy will dissipate. I think what you're starting to see is we don't know very much about it at all.
So all this stuff didn't fill us in that much.
We need help. We need some help.
Help may be on the way from a proposed new spacecraft expressly designed for supernova hunting. With a camera able to image thousands of supernovae at a time, the SNAP satellite would hugely increase the number of beacons out there measuring the universe's expansion. This might not only help find out what dark energy is, but also help answer what is perhaps the deepest question of all. Is there a reason why the universe turns out right now to be in almost perfect balance between the pull of dark matter and the push of dark energy? Or is the fact that dark energy didn't blow it apart in its infancy just a lucky accident? Maybe the Big Bang that turned out so well for us was just one big bang among many.
That if this burst of expansion happened here, there's no reason it wouldn't have happened here and there, and in the past and in the future.
Right, right. In the same universe.
In the same universe.
It was in what was the same, what started out in.
So now we need new language.
Yeah,
right?
yeah.
So the universe is a whole ball of wax, but they're different, disconnected pieces.
Right. It was like bubbles in a glass of champagne.
Exactly.
The champagne is the early, or a universe at any given time, or the multiverse.
Yeah.
And each bubble is a new universe.
It's a new universe.
If this is our universe, where would the other universes be in this multiverse?
Thanks for passing me the universe here.
Yeah.
We're actually kind of sloppy in astronomy when we talk about the universe, because what we usually mean is just the interior of this beach ball.
The part of the universe that we can observe is what we call the universe.
And that's, of course, strictly speaking, not true at all, because I don't have a single colleague who would entertain that space just ends here. You know, that there's a sign here saying space ends here. You know, mind the gap. We all believe that space goes on outside, and most of us believe that space actually goes on forever and is infinite, which means that there's another sphere like this, and in the middle of that, maybe there's another planet where people discuss their universe and can't see ours. And there's probably infinitely many of these.
If you have this ensemble of universes, there may be some basic things which are true for all of them, but there may be some quantities which are accidental in these different universes. Some of those universes will allow life to evolve and us to be here and speak about this, and some won't.
We said at the outset that our universe just got a whole lot weirder, dominated by matter we can't see and a force we can't feel. But maybe it's even weirder than that. Not only are we not at the center of our universe, maybe we're not even in the only universe, just in one in which dark matter and dark energy fought each other, at least when it mattered, back when the stuff we're made of was created, to a standstill. Come visit us at PBS Online. Scientific American Frontiers can be found on the World Wide Web at pbs.org.